In the last video, we saw that we could use formal charges to discard some of the candidate structures that we might get after we share lone pairs on neighbors. When you do this step, very often you're going to get multiple different structures that all look feasible. They all satisfy the octet rule. And it's only when you check the formal charges that you can tell whether or not you can discard some. But now we're going to look at an example where we can't actually discard something because the candidate structures are all equally good. Let's look at the carbonate ion. This will also be one where we've got a -2 charge on it, and that's going to change how we count the valence electrons a little bit. We have to count those extra 2 electrons that we're throwing on top of this. All right, let's go through the recipe. Draw the skeleton structure. If I look at the periodic table, carbon is closer to the center of the table than oxygen. So my skeleton structure for step 1 is going to look something like this. It doesn't matter where I put the oxygens, as long as the carbon is in the center and the oxygens are on the outside. The second thing I'm going to do is count the valence electrons. Well, let's see. I have 3 oxygens. How many valence electrons does each oxygen have? Look at your periodic table. For that column, oxygen is in the column with 6 valence electrons. And now for carbon, it's in the column that has 4 valence electrons. But I've got to remember that if I have a charge on here, I have to adjust the number of electrons. If this is -2, it means I have 2 more electrons to work with than I would have had otherwise. Now, if that were a +2, it would mean I'd have to take away 2 electrons. So be very careful with things that have charges on them. They are going to affect your step 2. You have to adjust your count of electrons for the charge that they give you. So what's it going to be? 18 and 4 is 22 and 2 is 24, right? That's how many electrons I've got to deal with. Step 3, connect the structure. All right, here's my skeleton. And I'm going to connect it by drawing a stick between the central atom and each of the outside ones. How many electrons did that cost me? Each stick costs 2 electrons. 2, 4, 6. So I've got 18 electrons left. Step 4, satisfy the outer atoms. Now each of those oxygens has got 2, so each of those oxygens wants 6 more. Let's see if we can give them 6 without running out. Okay, 1, 2, 3, 4, 5, 6. Now that one's done, it has 8. 7, 8, 9, 10, 11, 12. That one's done, it has 8. 13, 14, 15, 16, 17, 18. So I've used up 18 electrons, I got none left. This is my structure at the end of step 4. All of the outside atoms are satisfied. 5. Dump the remaining electrons on the central atom. Well, I don't have any remaining electrons, so I can't do that. Is the central atom satisfied? Well, no. It's got 6 electrons. It wants 8. It wants 2 more. So if it's not satisfied at this point, I have to share lone pairs with the neighbors. Now, if I took a lone pair here and put it down here as a stick, that would do it. Then it would have an octet. Let's do that. Then I'll have a double bond there. So this is the structure that I have at this point. Okay, everything has an octet. But there's another way that I could do that. I could have taken a lone pair from here and put a double bond there. If I had done it that way, I would have gotten this structure. And you can see where I'm going with this. I also could have taken a lone pair from this one and made a multiple bond facing down that way. Now we can't just say these are all the same structure because, I mean, if you take this one and you spin it 120 degrees, you'll get this one. And if you spin this one 120 degrees, you'll get that one. We can't just say that because if I look at any one of these structures, they have a double bond and two single bonds in them. And we're going to see that that turns out not to be right. Sorry about that. So here are my three candidate structures. Are there any that I can get rid of? Well, I'm going to do step 6 here, and I'm going to check the formal charges on these things. All right, if I look at this oxygen, remember formal charges are the number of valence electrons the atom has minus the number of sticks and dots. Oxygen has 6 valence electrons minus 1, 2, 3, 4, 5, 6, 7 sticks and dots. That's got a -1 charge on that oxygen. And if I look at this oxygen, it's going to be the same thing. It'll have a -1 charge. What about this oxygen? It's going to have 6 minus 1, 2, 3, 4, 5, 6. I'm counting sticks and dots with that second number, not electrons. So that is a 0 formal charge. And how about the carbon? Carbon has got 4 valence electrons minus 1, 2, 3, 4 sticks and dots, which is a 0. So it looks like I have a 0 on one of the oxygens and -1s on the other two, and a 0 on the carbon. Let's double check and make sure that that's a reasonable way to assign the formal charges. How? Well, all of the formal charges have to add up to the total charge. Now in this case, the total charge is -2. So these all have to add up to -2, and they do. 0 plus 0 plus -1 plus -1 is -2. Now if I go and assign the formal charges to these, I see something kind of funny happen. Let me just do it real quick. Now look at this one. It's got the same set of formal charges that this one has, 2 -1s and 2 zeros. I can't really say that this one's better than this one. They both have pretty much the same formal charges. They're just moved around a little bit. And the same thing with this one. There's a -1 formal charge there and there. There's a 0 formal charge there, and there's a 0 formal charge there. So now I have 3 structures, and none of them are any better than the other ones according to formal charges. So what do I do? What I have to do is keep all 3 structures. And I'm going to write them down again. I'm going to have to keep this one. So I'm just copying that one over again. Now it has a charge on it. When I have multiple, there's 2 times that I put square brackets around the entire structure. When I have a charge on it, and I also am going to do that when I have multiple versions of the same structure. And what I'm going to do is I'm going to tie that with the other versions with a double arrow. So we're at a double arrow in there. Now I'll draw this structure here. And now I have to do the third structure. It is really kind of tedious to have to do this, but I'll show you why it's important in a minute. Here's the thing. No single one of these 3 structures is correct. If I look at a carbonate ion, all of the bond lengths are equal. Now, we said before when we were introducing multiple bonds that when you have a multiple bond, it's shorter than a single bond. So it should be lopsided. This arm should be shorter than the other two arms, but in fact, all three arms are the same length experimentally. And by writing the structure out here, I can see why. Each of these bonds, the true structure, is an average of these three structures. So if I look at this bond, it's a double bond here, a single bond here, and a single bond there. That means it's an average of a double bond, a single bond, and a single bond. So what would it be? If you average a double bond, a single bond, and a single bond, average them by dividing by 3, what do you get? You're going to get 4/3. You get a bond and a third. So really, the bond between the carbon and the oxygen is 1 1/3 bonds. It is possible for you to have bonds, bond orders, we say, that aren't integers. So this is a case like that. You have a bond and a third, and all of the bonds are the same in this. If you look at any one of these, you'll have 1 1/3 bonds between the carbon and the oxygen. This situation is called resonance. You'll see on a future worksheet, the next worksheet in fact, will ask you, do you have resonance or not with a structure? You will have resonance when you can form multiple structures that have equivalent formal charges. Then no single structure is correct. You have to say the true structure is an average of these three, and you have to show somebody what all three of them look like. You've got one on your worksheet that's like this. It's the NO3-. And it turns out to be this exact same situation that I've just worked out for you here. It looks just like that. Resonance is important also because it makes very stable structures. If you've got resonance structures like this, and each of these are called resonance structures, we say we have 3 resonance structures here. If you've got resonance, you have an especially stable structure. And it is possible for you to take a molecule that is kind of mean and nasty and would be unstable for other reasons and make it stable by seeing that it has resonance. You can see why things like free radicals, which we'll talk about in the next worksheet, can actually be stable for a short period of time.